It's recording. Okay. Welcome to the CERIAS computer security seminar from Purdue University. Our speaker today is Professor Ian Goldberg from the University of Waterloo, and he will talk about Sphinx, a compact and provably secure mix format. Okay, Ian.
Thank you very much.
That's my seat.
Okay, this is joint work with George Dinazis of Microsoft Research, and if you want more information about what I'm going to be talking about today, this was a paper in the IEEE Symposium on Security and Privacy a few months ago. So I'm going to be talking about first mixed networks, what they are, then mixed formats, a particular aspect of mixed networks. I'll be talking about Sphinx in particular, the mixed format that we'll be presenting, do a brief outline of its proof of security, and then conclude. So first off, what is this mixed network thing? You may not have heard of it. So the idea of a mixed network is to enable a user, say Alice, to be able to send messages over the internet without automatically revealing her identity or her location. Okay? So why might we want to do this? Well, this is good for a number of reasons. For example, people who want to discuss sensitive topics, something like sexual assault survivors or cancer survivors, support groups, stuff like that. Whistleblowers who want to protect themselves against retaliation. So you're an employee at a company, you want to notify somebody that your company is leaking toxic waste into the river over here. You want to do that without your company finding out that you're talking to the Environmental Protection Agency, for example. Quite recently we saw examples of this latter where reporters or dissidents or citizens in certain countries might want to be protected when they communicate with people outside. So we saw this happening in Myanmar in 2007, and we saw it happening very recently, just in June, in Iran. Okay, we had people talking, wanting to communicate and getting their message out, where the people who run the network, the government or people controlling the communications in some way, are the people they want to protect themselves from. Okay? So, a simplistic solution that was used in the early 90s is just to send a message to a trusted friend and have that friend strip off your name and forward it on for you. Okay? And it doesn't have to be a friend, it could just be some person running a service that does this. So, as I said, this was used in the early 90s, and the problem is that this requires that the relay is trusted. So if you do this, send it to the relay strips off your identifying information and sends it on. This has the problem that the relay itself knows who you are and who you're talking to and what you're saying. Okay? And this can be an issue. One of these relays that was used in the 90s was called a non-penet phi. And that the 90s might be before some of your times. I guess if you're grad students, you might be familiar with this. Freshmen this week probably would not be familiar with this. But what happened was, so a non-penet phi allowed you to send messages through it, and whenever I sent an email message through it, it would see my name, check a list, and if I'm not already in the list, it would add me to the list and assign me a random number ID, so a non-25549 at a non-penet phi. Okay? And then it would send the message, making it look like it came from a non-25549 at a non-penet phi. That way, replies to the message would go to a non-penet phi would say, oh, this is a reply to a non-25549, looks up in the list, oh, it's Ian, and here's his real address, and it will send the reply to me. So a non-penet phi had to maintain this list, this mapping, between real people, real email addresses, and they're anonymous pseudonyms. Okay, they're pseudonyms anon25549, whatever. Okay, so what happened in the 90s was that somebody used anonpennet-fi to send some work from a certain church that will not be named, that you might know who it is, and that church claims copyright over their scriptures. And anyone who posted those scriptures to the internet kind of got in trouble. And so someone did it anonymously, and they wanted to find out who it was. So they sued Johan Helsingus, the operator of anonpennet-fi, and in court tried to get him to turn over this list. And Johan luckily managed to prevent the turning over of the entire list, but could not prevent the turning over of just the 2 addresses in question. Okay, so he had to turn over part of this list. And then he just shut down his service because he said, if I can't protect my users against an attack like filing a lawsuit, then I'm not going to run the service, because I can't, in good conscience, run the service when I know my users could be outed very easily. As it happens, the users of this service, in this particular case, were a little bit clever, and the addresses that were turned over were just addresses of other remailers. So in fact, this idea of using multiple remailers is a good solution to this problem. So instead of sending the message just through one relay, we send it through a whole path of relays. Okay? And this alleviates not only the trust problem, but also other network issues like load balancing. So not all messages over the internet are going through this one central point. Right? So let's look at a picture of how mixed networks work. So here we have a picture of Alice and Bob. And these swirly things in the middle are meant to represent mixed nodes. So there are a number of mixed nodes, which are servers spread throughout the internet. Alice wants to send a message to Bob without revealing to Bob her identity or her location. So what Alice does is she picks a number of mixed nodes to form what's called a path. Okay, in this case, Alice picks 3 mixed nodes that you may be able to see in yellow, but the arrows point them out. And then Alice constructs her mixed message. And her mixed message contains basically her message wrapped in a layer of encryption, wrapped in another layer of encryption, wrapped in another layer of encryption. Okay? And we're going to visually represent this encryption by envelopes, as is often done. So Alice ends up with this envelope, and inside this envelope is another envelope, and inside that envelope there's another envelope, and inside that there's the message. Okay? So Alice takes this envelope and sends it on to the first mixed node. That mixed node opens up the envelope and pulls out what's inside. It's another envelope, and that envelope is addressed, and that envelope is addressed to the next remailer. So it sends it on to the next one, who opens it up and finds another envelope, and that envelope is addressed to someone else, that being the next remailer, so it sends it on. That remailer opens up that envelope, finds a plain message that is also addressed, and it's addressed to Bob, and it sends that message on to Bob. Okay? So that's how a mixed message at a high level gets from Alice to Bob. Now Bob, of course, just receives this message from Alice, from the last mixed node, and doesn't know that it came from Alice. Okay? Great. So, that last picture you just saw, some of you may have seen a very similar picture in another context, and that's of onion routing, or you may know Tor. Okay? Some people are nodding, they know about Tor, maybe you've used Tor. So what's the difference between what I'm talking about here and Tor? So the big difference is that Tor is meant to handle real-time traffic. Okay? So what happens in Tor